How many fish do you think are in the world's oceans? Millions? Billions? Try 3.5 trillion. And how many of those fish do we take out of the ocean every single year? 1.75 trillion fish, which is 50% of the global fish population. And this only accounts for fish caught legally. If we continue at this rate, our oceans will go from looking like this to something more like this. And a world that doesn't support fish doesn't support humans either. There are very few methods for effectively evaluating fish populations, and many of those methods are invasive and detrimental to fish health. Some current methods include by hand measurements, the use of stereo cameras, or laser calipers. All of these fail to effectively and efficiently capture fish length. This has left scientists with a lack of data, making it difficult to study fish populations. UCSD's Engineers for Exploration have spearheaded this problem with the development of FishSense. With its novel and compact design, the FishSense platform contains state-of-the-art technologies to image and measure fish. By combining the Intel RealSense depth camera D455 with model machine learning algorithms, our system is able to capture fish data, providing scientists insights about fish length and biomass significantly faster than hand measurement methods. My name is Maddie, and this summer I've been working to improve the performance of FishSense by upgrading the system hardware. We have decided to upgrade the system processor from a Raspberry Pi to the NVIDIA Jetson TX2. Upgrading the processor will allow us to process images at a higher frame rate and in real time. In order to upgrade the system, processor compatibility testing was completed. The TX2 processor was flashed and connected to Connectech's Orbity carrier motherboard, where it was then connected to the Intel RealSense depth camera. The RealSense SDK was downloaded and the C++ code was built and run. The system underwent various performance testing and a power analysis to confirm that the upgraded hardware is more robust. Functionality of the TX2 was investigated by accessing the TX2's GPIO pins and by SSHing into the TX2 without internet, which will make deployments run much more smoothly.
Hey guys, it's Raghav from the software side of FishSense, and as part of that team, that meant that I had to work on improving and integrating the model into the algorithm. Improving the model entailed that I had to decrease the number of false positives, such as from rocks and debris, while also increasing the accuracy of each and every bounding box to be more tightly bounded around each individual fish. As such, here are some pictures of the old model at work, and here is the improved model at work. As you can see, there are still some problems with some discrepancies here, but in general, the boxes are more tightly bounded around each and every individual fish, as well as the number of false positives is greatly decreased. With an improved model, I then worked on incorporating the depth data to make the measurement fully automatic. So the depth data is returned as a CSV, as seen here. Here's that same CSV colorized. And then what I do is I take the points from the corners of each and every bounding box, and then I just use some simple Pythagorean theorem, a squared plus b squared equals c squared, to find the length of the fish. So the algorithm has now spit out that the fish is about 0.35 meters, which is about 1¼ foot.
Hi, my name is Ronan Wallace, and this summer I worked on the software for FishSense. With the help of our collaborators at Scripps Institute of Oceanography, we were able to deploy our system at the Birch Aquarium, where we were able to collect a vast amount of valuable fish data. As you can see in the video, a scuba diver is handling our device, capturing both RGB and depth data simultaneously each second. With our camera, as mentioned previously, we are able to capture both RGB images and depth measurements. This allows us to detect fish and get their head-to-tail length and calculate biomass. From these calculations, we are able to understand fish health and population a little bit better without harming the fish or their habitat. We submitted a paper that was accepted to IEEE OES Oceans Conference for publication, detailing our device and how it works. And currently, We're writing another paper detailing our hardware and software upgrades using our newly integrated GPU, which will be submitted to the IEEE Embedded Systems Letters Journal.
Thank you so much for watching, and if you have any other questions, feel free to reach out to us or visit e4e.ucsd.edu for more information.